So today we are going to be talking about cascaded op-amp circuits. And the examples that I am going to work with you today are going to be negative feedback stages cascaded into each other, but that does not have to be the case. We can cascade positive feedback into negative feedback, open loop into positive or negative feedback, whatever. I'm just showing you negative feedback in this case so that we have a good understanding of what's happening. So cascaded op-amp circuits. And in order to understand what's going on here, we are going to look at a numerical example. Okay. So I'm going to have some input signal that I'm going to call V1 here, and I'll give it a number here in a moment. This is a resistor, and I'm going to call this a 2 kilo ohm resistor, I believe, if I can see my notes. Yeah. And then down here, I'm going to have my input voltage V2, and that is going into a 3 kilo ohm resistor, like so. This is an op-amp. I'm choosing to put the inverting input terminal on top. And I'm going to call this op-amp A1 because it's the first op-amp that we're going to have in this circuit. I'm going to choose to ground the non-inverting input terminal like so. And I'm going to apply negative feedback with a 5 kilo ohm resistor here. Connected to the output terminal of op-amp 1. So I'm just going to label this node as effectively Vout1. I'm going to connect another resistor. So this will be, a 4 kilo ohm resistor. And now I'm going to have my second op-amp A2 here. So I'm going to have a feedback path from the output of A2 to the inverting input of A2. That will be a 10 kilo ohm resistor. I'm going to measure the output voltage of op-amp 2 here as an open circuited voltage. So this will be Vout2. And I'm going to choose to ground this terminal as well. So this is my system, and this is a system that contains cascaded op-amp circuits. So realistically, anytime I use the output voltage from one op-amp to be the input voltage for a second op-amp stage, I have a cascaded system of op-amps, okay? So we're going to look at this circuit in two ways, okay? So first, let me define my voltage V1 as 3 volts and my voltage V2 as 1 volt. I think somebody said my name. Yes. So fantastic question, okay? So for this particular example, and I'll tell you essentially what's going on when we look at it in the second way. The reason why we might cascade op-amps together isn't going to be intuitively obvious until the end. Once we talk about how we can treat each individual stage as effectively a gain stage or an amplifier block stage, we could cascade op-amps together to perform complex mathematical functions. So say, for example, that I wanted to take the integral of 2 different signals and then add the results of those integrations together. I would need, in my first stage, integrating amplifiers And then in my second stage, I would need a summing amplifier. So I'm performing multiple mathematical operations by chaining these op amps together, okay? So another place that you might see cascaded op amps, and this is going to be one of either, I don't remember if it's a design project problem or if it's actually the design problem from your take-home test. I think it might be the latter, but I can just describe it to you now. Essentially, if you start out with a sinusoidal input signal, and you want to use that sinusoidal input to generate a square wave and a triangular wave, you might feed your sinusoidal input into a comparator because the output of a comparator would be a square wave. And then you could feed the output of that comparator into an integrator because a square wave integrated looks like a triangular wave. So you can do signal processing that way. But it's all about just performing multiple mathematical operations in a specific sequence. Okay. All right, very good question. So we are going to tackle this using a brute force method first. For this particular circuit, we're going to find out that it's not even necessary to do it this way, but I want to show you an example of it for how you would treat a circuit where you have cascaded op amps and you can't identify what the individual stages are, okay? So what I'm going to do is I'm going to introduce just a couple of other quick voltages here. So I'm going to call the voltage at this node V1 minus, because that's the voltage at the inverting input terminal of op amp 1. And similarly, I'm going to call this voltage here V2 minus. And so what I'm going to start doing is I'm going to apply KCL at the nodes where I have unknown voltages labeled. We're going to see that we're going to run into a slight problem here in a moment, okay? So when I'm applying KCL at this node V1 minus, I'm going to be adding this current together plus this current plus this current, right? So that might look like so V1 minus V1, which is 3 volts. So I'm just going to put in 3 volts there, divided by 2 kiloohms plus V1 minus V2, which I told you is 1 volt, divided by 3 kiloohms plus V1 minus V out 1 over 5 kiloohms is equal to 0. So we've got one equation there. And now I'm going to apply KCL here at my output node. Just to be clear, I don't want you guys to write this down because it's going to break everything. So I'm going to erase it and do something else in a minute. I'm just not trying to waste your time. I just want to show what's going on. So if we try to apply KCL at V out 1, the current that's flowing up through the feedback path is pretty easy to figure out. That's just going to be V out 1 minus V1 minus over our feedback resistance, which was 5 kiloohms. The current flowing to the right through that 4 kiloohm resistor would be V out 1 minus V2 minus over 4 kiloohms. And then we have the current flowing to the left. Okay. So most of the time when I ask students to apply KCL at this output node, they would tell me that I would just add those two guys together and set them equal to 0. Nikolai, you're shaking your head as if that's incorrect. So would you care to volunteer why you believe it's incorrect?
My way of thinking about it would be looking at the practical op amp and doing KCL around that to find it going through our V out node.
Sure.
Which, if we were to look at that, I would think it would have to go through that dependent voltage source we have
Mm-hmm.
and our resistance node. Or if we had a load.
Yeah.
Go through that as well.
Absolutely. So essentially, if we use the practical op-amp model, it would be very easy to see that the current that I have drawn flowing into the output node should be non-zero. But I would need to know what the open loop voltage gain of the op-amp is. I would need to know what the output resistance of the op-amp is, et cetera, okay? So a more simplistic way to think about it, but I think it's a little bit easier to understand here, is our ideal op-amp relationship says that no current can flow into or out of the input terminals of our op-amp, but it does not specify that no current can flow into or out of the output terminals of our op-amp. So we don't have any real reason to assume that that current is zero. If we're using the ideal op-amp model, because we have negative feedback circuits here, I haven't specified open loop gain, input resistance, or output resistance or anything. Essentially, we just can't apply KCL at this node because we're not provided enough information. So we need to find another relationship that will get us through. So we'll sort that out in a moment. So KCL at Vout1 literally cannot be done, okay? And we can't apply KCL at the output node of any op-amp circuit when we're dealing with ideal op-amps because we don't know what the open loop voltage gain is or the output resistance or anything like that is, so that we literally cannot quantify the current that's flowing into the output node in terms of the information that we do know. So we just need to find something else, okay? So I'm going to move over to the non-inverting input node for amplifier number 2, right? So that would be this current flowing to the left plus this current flowing up, because we know 0 amps is going to flow into that input terminal. So let me just get rid of this stuff and change this to be KCL at V2 minus. So our current flowing to the left is going to look like V2 minus V out 1 over 4 kiloohms. And our current flowing up through that feedback resistor is going to be V2 minus V out 2 over 10 kiloohms. And I'll set this equal to 0. And this is my second equation. Okay. So I have 2 equations and 4 unknowns currently. So I've got to figure out where the heck these other 2 equations are going to come from. And the short answer is, well, we haven't yet applied to the second ideal op-amp rule. So that's where those guys are going to come, right? So that voltage V1 minus is the same as this voltage here, V1 plus, which is quite obviously 0 volts. And that voltage V2 minus is the same thing as this voltage here, V2 plus, which based on what I've drawn, is also 0 volts. So if we replace this V1 minus with 0, and this V1 minus with 0, and this V1 minus with 0, we actually have a 1 equation, 1 unknown system where the only thing we don't know is V out 1. So we could solve this guy for V out 1. And when I solved it, just using the numerical solver on my calculator, I got that V out 1 was equal to negative 9.167 volts. Now down here in my second equation, V2 minus is 0. V out 1 is a known quantity, and so I can solve this guy by plugging in the value of V out 1 and solving for V out 2. And I wound up getting 22.917 volts. Okay. So this is the brute force method of solving this system. Now let's talk about an easier way to do it, okay? So I'm going to scroll down here and I'm going to redraw my circuit. So here is my voltage V, sorry, that should be V1. This is a 2 kilo ohm resistor. Here's V2. This is a 3 kilo ohm resistor. Here's my op amp A1. Inverting terminal, non-inverting terminal. Grounding this guy yet again. Feedback path. I think this was 5 kilo ohms. Here's that voltage V out 1 again for what it's worth. Here's a 4 kilo ohm resistor. Here's my amplifier A2. Ten kilo ohm resistor. V out 2. Let me ground this guy like so. Okay. So what I'm going to do, and I want to be clear here, this method does not always work. We have to be able to recognize what each of these stages is in order to do this. So in one of your homework problems, I give you a circuit like this where I have feedback connected from the output of op amp 2 to the input of op amp 1. We've never seen that before, so we have to use the brute force method for that guy. Okay, but anyway. So what I'm going to do is I'm going to just draw a dash line here at the output pin of op amp 1. And I'm going to call everything to the left of this dashed red line stage 1. And I'm going to call everything to the right of this dash line stage 2. Okay. So what I want you guys to do for a moment here is literally ignore everything to the right of that dashed red line. Okay, so stage 2 does not exist. If stage 2 doesn't exist, what type of amplifier is stage 1? It's a weighted inverting summer. Okay, absolutely. So we have multiple input signals applied to the inverting input pin, and we're just trying to find the output voltage. So this is nothing more than a weighted inverting summer. And so we know just by looking at this thing that V out 1 should be negative 5 kilo ohms times V1 over 2 kilo ohms plus V2 over 3 kilo ohms. Plug in our numbers for V1 and V2 and tell me what you get, please. Negative 9.1666 repeating, right? So negative 9.167 volts. The exact same result we got from our brute force method, but I would argue that that was much easier to figure out because if we know how this stage operates, we don't have to do any circuit analysis at all. That was the whole point of going over all of those common topologies. get rid of the analysis and just it behaves this way because it's this type of amplifier. Ignoring stage one, what kind of amplifier would stage two be? Where essentially we're just taking that output from V out one and saying that's our new input voltage for stage two. So treat the left-hand side as if it were a voltage source having a value of V out one. What would this be? Just an inverting amplifier, right? So we would have the relationship V out two is just negative 10 kiloohms over 4 kiloohms times V out one. Plug those numbers into your calculator. $22.9167, the exact same result we got earlier. So this method of breaking the chain of amplifiers or the cascade of amplifiers into individual stages makes analysis of cascaded op amps incredibly simple as long as you can recognize what each stage is.
For us to be able to split into different stages.
Literally just put that dashed line on the output of each op amp and then see if you recognize what's to the left.
And the reason why we couldn't do the one in the homework was because it was in an entire loop.
Yeah, so if I were to, for what it's worth here, I'm just going to scribble this on top kind of real quickly. So if I had a feedback resistance connected, I'm just going to call this RF, from the output of amplifier 2 to the input of amplifier 1, that's nothing that we've ever seen before. And so we can't just use these stages. In your much later classes, you will learn of a technique called the Miller method that would allow you to split that feedback resistance up and apply some of it on the input side of amplifier 1 and some of it on the output side of amplifier 2. But in order to understand how that works, you need to know way more network theory than you currently know, which is effectively zero. So we'll leave that for electronics, but it is a very common practice of using the Miller method to break up feedback between multiple stages so that we can just look at them as here's what stage 1 is going on, fed with this Miller impedance. Here's stage 2 loaded by this Miller impedance. So that's a problem for another day. Okay, so based on what we know these two stages are, what's the purpose of this cascade operation? Just ballpark it here. So I have a weighted inverting summer that's being fed into an inverting amplifier. So my output is just a weighted summer, effectively. I got rid of the fact that the inverting summer is always going to change the polarity of my output signal by just cascading that into a second stage that changes the polarity back to positive. So that's a very simple application of cascading things together to just get rid of a negative sign because sometimes that's important. In one of your design prompts, I have you design effectively a binary to base 10 converter. And the second stage of that binary to base 10 converter should be an inverting amplifier with a gain of -1, just so that your output of your thing that's flipping through all of your different binary numbers, which is just going to be a weighted inverting summer, gets flipped to a positive number so that when you put in 1, 0, 0, 0, you don't get out -8, you get out +8 kind of thing. So anyway, so this is cascaded op amps in a very simplistic sense. As I said a couple of minutes ago, this particular example happens to do two negative feedback op amps cascaded into each other. You can cascade positive feedback into negative feedback and vice versa, open loop into either type of feedback, it doesn't matter. These same basic-ish rules apply. If you know what one op-amp stage is doing, just use those relationships. The second op-amp stage, use those relationships. And anytime you don't know what it's doing, then you have to use that brute force method. So let's now look at what's called an instrumentation amplifier, which is a special amplifier used in a lot of practical applications. And it happens to be an example of a cascaded amplifier system. So I want to preface this by saying, usually when you have an instrumentation amplifier, this is a single chip. So all of these op amps that I'm about to draw are internal to the IC itself. And actually the resistors that I'm about to draw as well are internal to that chip. So we may not have control over them. I just want us to understand what's going on. Okay. So instrumentation amplifiers are, for lack of a better word, it's almost like a comparator for small signals, except that we want to actually be able to linearly amplify those small signals, okay? So we're gonna have access to an input terminal, two input terminals and an output terminal. We are not going to apply any sort of feedback. So like on a big picture scale, it's going to look like a comparator, but the applications are for very, very small voltages generated by things like thermocouples, nickel strain gauges and stuff like that, where typically speaking, you have a large DC or DC component of your signal and a very small changing component. And this is used to boost the level of that small change that you would see, okay? These are used in a lot of medical devices, scientific instruments, and they are used all over industrial control systems, particularly taking sensor data and converting it into usable signals. Okay. All right. So, giant schematic diagram. So here's my input signal VN1. And I'm applying this input signal to the non-inverting input terminal of an amplifier that I'm going to call A1. And then I'm going to connect the output of A1 back to the inverting input of A1 with just a wire. Here's a resistance that I'm going to call R1. And then down here, I'm going to branch off this is going to be the inverting input terminal and the non-inverting input terminal of amplifier A3. And I'm going to have negative feedback connecting the inverting input of A3 to the output of A3 like so. And I'm going to call this resistor R2. And then I'm going to take my output signal V out 3 here. So this is the output of the amplifier system as a whole, okay? Down here on the bottom side of things, I'm going to have pretty close to a mirror image of what I have on the top side, except for one distinct difference. So I'm going to show you that difference first. Instead of having feedback down here, which would make this a positive feedback system, which would mean I couldn't have linear amplification, I'm actually just going to take this resistor R4, and then I'm going to just ground out that leg. Working back towards the left, here's a resistor R3. And now I have my op amp A2. Where I'm going to put my my non-inverting input terminal on top, my inverting input terminal on bottom. I'm going to apply VN2 here, and I'm going to use negative feedback through literally just a wire to connect the inverting input of A2 to the output of A2, like so. So this big thing right here is the representation of an instrumentation amplifier. And you could build your own instrumentation amplifier if you were so inclined, using 3 physical op amps. Generally speaking, the op amp A1, A2, and A3 would all be identical op amps in that case, so that they all have the exact same electrical performance. And so what I want us to do is to take the time to figure out how our output voltage Vout3 is related to those input voltages VN1 and VN2. Okay. So what would the voltage at that node be? Let's start there. I disagree. So it will be equal to VN1, right? So pretty similarly, what will the voltage at that node be? VN2, okay? Now, I'm going to call this voltage right here V3 minus. I'm going to call the voltage at this node right here V3 plus, okay? So what I'm going to do is I'm going to perform KCL at that node V3 plus, and we're going to see what shakes out of that, okay? So that would be this current flowing to the left plus this current flowing to the right, since I know using the ideal op amp model that no current will flow up into that non-inverting input pin. And so that's going to look like V3 plus minus VN2 divided by R3. And then I'm going to have plus V3 plus over R4 is equal to 0. Now, I know that since we have a negative feedback system, V3 plus is going to be exactly equal to V3 minus, okay? So I'm going to solve or rearrange this expression and solve for having just V3 plus is equal to something in terms of VN2 here, right? So if I pulled out my common factor of V3 plus, I would have V3 plus multiplied by 1 over R3 plus 1 over R4 is equal to VN2 over R3. When I divide both sides by 1 over R3 plus 1 over R4, what does that look like? Well, essentially, yes, it's going to come out looking like voltage division. But it was specifically what I was asking here. So 1 over R3 plus 1 over R4 is just R3 in parallel with R4, right? So I'm going to wind up having VN2 over R3 multiplied by R3 times R4 over R3 plus R4, and the R3 in the numerator and the denominator are going to cancel each other out, and I'm going to wind up getting V3 plus is equal to Vn2 multiplied by R4 over R3 plus R4, which is exactly the voltage division relationship that we would have trying to solve for V3 if just Vn2 was the voltage, the known voltage drop across those two resistors in series. And that seems like a reasonable result here, considering that we know that no current is going to branch off and flow through there. Effectively, that voltage Vn2 just sees R3 in series with R4, and we're looking for the voltage drop over R4. So voltage division is just a different way to get this exact same result. Okay. So now let's do KCL at V3 minus. So at V3 minus, we are just going to be adding these two currents together. So that's going to look like V3 minus minus Vn1 over R1. And we're going to have V3 minus minus V out over R2. Let me double check that. Yep. And this is going to be equal to 0. And all I'm going to do now is I'm going to substitute in what I have for V3 plus everywhere I see V3 minus, since I know that those two voltages are equal to each other because of the ideal op-amp rules. So that's going to look like Vn2 multiplied by R4 over R3 plus R4 minus Vn1 all divided by R1 plus Vn2 multiplied by R4 over R3 plus R4 all over R2 is equal to V out 3 over R2. And so what I can do is just multiply both sides through by R2 to get V out. So that would give me the relationship V out 3 is equal to, so I'm going to have V in 2. So I have V in 2 times R4 over R3 plus R4. And then I have a factor of 1 over R1 that's being multiplied by R2. So I'm just going to write that as R2 over R1, like so. I'm going to have minus Vn1 times R2 over R1. And then when I multiply that second term of Vn2 times R4 over R3 plus R4 all over R2 by R2, I just get rid of that denominator. So I'm going to have plus Vn2 times R4 over R3 plus R4. And I can pretty this up a little bit because I have a common factor of Vn2 times R4 over R3 plus R4. So I could choose to express this as Vn2 multiplied by 1 plus R2 over R1 times R4 over R3 plus R4 minus Vn1 times R2 over R1. So I have a result here that gives me V out in terms of V in one, V in two, and the resistors that we used. Usually in an IC based instrumentation amplifier, the ratio of R2 over R1 and R3 over R4 are equal to each other. So let's say that if R4 over R3 is equal to R2 over R1 is equal to K, where K is just a scaling factor, then our result would simplify to V out 3 is equal to V in 2 times 1 plus K over R4 over R3 plus R4 minus V in 1 times K. Okay. So we're going to simplify this a little bit more. I'm going to scroll down to the next page to do a little bit of algebra. Why are you laughing at me, Nikolai?
It simplifies so much from so big. We're gonna thank them on homework, just, oh yeah.
Yeah. So I have R4 over R3 plus R4, right? I'm going to choose to flip that upside down real quick and play around with it algebraically, okay? So if I have R3 plus R4 over R3, that would be the same as 1 plus R4 over R3, which is just 1 plus, actually, I'm sorry. I should have had a R4 here. Sorry about that. So let me try this again. My mistake there. So I'm going to have a factor of R3 over R4 plus 1. So that's 1 plus 1 over K, which would be the same thing as K over K plus 1 over K, or 1 plus K over K. So when I flip that guy back around, this is going to look like V in 2 times a factor of 1 plus K times a factor of K over 1 plus K minus V in 1 times K. And hopefully pretty obviously this guy cancels this guy, and I can pull that factor of K out so that I'm left with K times V in 2 minus V in 1. So let me ask you guys a question. Does that output relationship look familiar-ish? It should look like something from Monday's class. Go back to your Mondays when we talked about the common op-amp topologies, right?
Differing.
A differencing amplifier, exactly right. So don't write this down, it's not important. I'm going to copy this and then we're going to look at it from that second perspective. So I'm going to put a box around this part right here. And I'm gonna put another box around this part right here, even though they're essentially identical. And then lastly, I'm gonna put a box around the remainder of this guy. So in that red box, we have what's called a unity gain buffer. So essentially, that is a non-inverting amplifier where my feedback resistor is 0, and that resistor R1 is an open circuit or infinity, so it gives me a gain of exactly 1. So even though it doesn't really look like something we've seen before, it is a special case of something that we've seen before. So this is, like I said, the unity gain buffer. And in a unity gain buffer, V out is equal to V in. That's why it's a unity gain system. The voltage gain is just 1, right? Exact same thing is true for this guy. It's just a unity gain buffer that was flipped upside down. So everything in the red block is a unity gain buffer. Everything in the green block is a unity gain buffer. And then if we just look at what's in the blue block, where R1, where R1 is equal to R3 and R2 is equal to R4, it is literally the differencing amplifier that we derived the relationship for in our last class meeting. So we could, if we had broken this guy up into individual stages, literally not worried with any of that algebra and come out with a relationship. V out is going to be equal to R2 over R1 times Vn2 minus Vn1 if we were paying enough attention. So now I have concluded my lecture on cascade amplifiers.
If like there's 4 op amps connected, could we stage all 4 of them? if
Sure.
needed?
Yeah,
There's no limit to that or at all?
no, not at all. So I say there's not a limit at all. So obviously the rules about your output can never exceed your supply voltages and all of that kind of stuff are still true. So like if you had 5 gain stages connected to each other to where you had an overall voltage gain for your system of like 10,000, that's not just going to magically allow you to put 1 volt in and get 10,000 volts out because you've got 5 of them together. You're still going to get an output voltage that's limited by VCC plus, or can't be more negative than VCC minus. You can't break those rules. But other than that kind of thing, yeah, just you can do whatever math you want with these. That's literally the point of them. Yes.
Why did they show up those red and green boxes?
So we didn't short them. They are shorted. But that gives us a unity gain configuration. Okay. So that is a way for this amplifier to force the output of that buffer stage to be equal to the input of that buffer stage. So we talked about the reasons why we might want to do that in our last class meeting when we were specifically talking about the non-inverting amplifier and the special case where our feedback resistor was much smaller than the resistor we placed between the inverting input terminal and ground. So whenever we have a sensor that does a good job of producing an output voltage, but a very poor job of sending any current through, we want to use unity gain buffers in order to reproduce that signal without having the effects of any loading impedances drawing that voltage down. So that's why this particular guy is used in applications where we're going to have incredibly small AC signals that we're trying to boost. It's going to actually wind up rejecting the DC signal because the DC signal is applied on both sides. So they're going to subtract from each other, and only the difference of the AC part is going to survive the amplification. So anyway, we're done with op amps. So, we're gonna start on transient analysis circuits on Friday's class meeting. We're still gonna move along, but I want to be clear, your exam is not until Monday. And I will try my absolute damnedest to get my head out of my ass and get your homework assignments on this material and stuff posted so that you can practice it before your test.